Assalamu alaikum. In today's video, I would be discussing about shell models. So, what are the use of these shell models in case of ATOMSK? So, mainly we would understand how we can simulate polarizable ionic materials. So, what does this term mean? Polarizable ionic materials. You already know that when two elements are connected by an ionic bond, we define them as ionic materials. In case of such ionic materials, if we can separate the charges, that is the charge of the core, that is the nucleus, and the charge of the electrons by a certain distance, then we can say that that particular ionic material is polarizable. So to understand and study those kind of systems or materials, we have to take the help of ionic core shell models. So these were first introduced by Dick and Overhauser in 1958. And in these ionic core shell models, there are mainly two parts. Firstly, the center, or we can define them as the core. In this core is the massive, or this core contains the almost the total mass of this system. Also, there is a charge in the core. This charge is defined by capital Q. Moreover, it is positive charge. And in the shells, there are also charges, but the shells do not contain a lot of mass, so they are sometimes massless or with very little mass. And in the shells, there are mainly negative charge, which we define as defined with smaller q. Next, how ATOMSK deals with ionic core shell models. So what ATOMSK does is it mainly helps to add charges or add shells to existing rock salt lattices or existing ionic materials. Moreover, with the help of ATOMSK, we can also calculate the electronic polarization that is occurring within the system. So we can also what we can do other than that, we can add shells to existing systems. For example, you have an ionic material, that is sodium chloride. Now you can add shells to this sodium chloride material. You can save this total system after adding the shells into the file format .gin or DL poly formats. This is very important because you cannot save the file in a XSF file format, because if you save this in an XSF file format, the XSF file format does not allow you to read those shell positions. Okay, so you will understand this when we go to the demonstration portion. Next is the shell placement and polarization. So with the help of ATOMSK, you can calculate the polarization that is happening within the system. The other things you can do is selective shell addition. For example, you want to add shells but not for all the elements. For example, you have a system of sodium chloride structure. Now you want to add shells, but you want to add the shells to only chlorine elements. So you have the option to add shells selectively. Moreover, you can also remove shells, and in case of removing shells also, you have the option to remove shells from the whole system or remove shells selectively. The next is defining electric charges for cores and shells. So how you can do this is, firstly you write your charges in a text file, then you read the text file and you read that into ATOMSK. Next is calculating electric polarization in ATOMSK. So if you have already added your shells, added charges to that shells, now you can compute the electric polarization of your existing system. However, if you have not added your charges and you want to calculate the electric polarization, then after adding the charges, you have the option to calculate the electric polarization. So what does the calculation of electric polarization mean? In this case, mainly when your when the charges of your center or the core and the charges of your shells are separated by a certain distance, then polarization occurs. So the amount of this polarization, mainly the amount of the distance between these two particular core and shell, can be calculated with the help of ATOMSK. What is the significance of this calculation? So you see, in case of a ionic core shell model, sometimes we need to study how these models behave under a certain condition, for example under a certain electric field. So this kind of study is very important, and in these cases of studies, calculating the electric polarization helps us in studying these things. Next, handling shells with subsequent options. So you already know about options, and there are a variety of options which can be applied to a system. So there are the cases of general compatibility. In cases of general compatibility, like we can apply options like shift and duplicate without any hiccups. For example, we can shift our entire system. By entire system, I mean that both core and shell, the total system can be shifted or duplicated easily. But there is the special case of wrap, because we know what wrap does. What wrap does is, if some of your particles goes outside of the simulation box, then with the help of wrap we can bring those particles or elements back inside the simulation box. So in case of ionic core shell models, what happens is, if your element goes outside of the simulation box and when we apply the option wrap, the whole system does not get back into the simulation box. Rather, the wrap only works on the cores. Okay, so your cores get drawn back into the simulation box and your shell might still remain outside of the simulation box. So it is a special case which you need to keep in mind. Now we will go into the demonstration segment of this video. So firstly, we will start with opening a terminal. Then we will create the rock salt structure. ATOMSK -- create rock salt of the element sodium and chloride. Sorry, I need to input the lattice parameter first, then sodium chloride, and saving it into XSF file format. So our rock salt structure is already created with the default orientation of 100, 010 and 001. So there are 8 atoms in our structure. Next, what we want to do is adding shells. So in case of adding shells, we are calling our previous file, XSF file. Next, we are adding shells, add shells. We are adding shells to all the atoms, sodium and chlorine. So we are using the keyword all here, and we are saving our structure in NaCl underscore shells dot XSF. So you see, here is a warning: data contains ionic shells which are not supported by some output formats. Shells will be lost in some output files. So this is very important, because if you want to read your structure with the help of this, you will see that there are no information about the shells you have added, which means the information about shells have been lost. So what you need to do is, you have to store your information into .gin file. So I am again opening the XSF file, adding shells to all the atoms and storing the output in shells.gin. So you see, now there is 8 shells were added to the system, writing output file 8 cores plus 8 shells. Now if you want to look at the output, you see there in this output there is the position or the information of these cores sodium core, sodium shell. So there are 4 sodium cores, which means that there are 4 sodium atoms and 4 chlorine atoms along with the shells for those particular cores. And these 3 columns mainly indicate the XYZ position of the particular cores and shells. So this is very important, because by gathering information of the position of the core and shell, we can understand whether it is in a polarized state or not. Because if they are in a separate position, we can understand that they are polarized. Okay, so we have already created our structure, we have added the shells. The next stage is adding charges to those shells. So for adding charges, we can use this text file. In this text file, firstly we have to use the keyword charges, next sodium. Then you can see I have used 1.2. This 1.2 is mainly for the core and the minus 0.2 is for the shell. Again, for this chlorine, we have used minus 0.8 and minus 0.2, which means the first number is for the core and the second number is for the shell. So this can be seen after we have added our charges ATOMSK. We are opening sodium chlorine dot XSF. We are adding shells to all the elements. Then under the properties keyword, we are charges.txt, adding via charges, and we are storing our output in NaCl underscore shells.gin. So the input file is the number 1 file, and we want to overwrite our previous structure. Now if we take the output, okay, so you see there is a separate column here which indicates the charges of the particular core and the shells. Next, if you want to calculate the electric polarization or the electronic polarization, you can do that with the help of ATOMSK. So ATOMSK electronic dash polarization, we are running this on the gn file .gin. There was a mistake here, so this is particularly a mode ATOMSK double dash. Okay, so we have created and the output was written in .cfg and .xsf file format. Now we can just open those two. After opening, you will see that firstly the information about the simulation box is given. Next, you see that there is no velocity. No velocity indicates that there were no velocity components in this particular output file format. Then you see that the entry count is 7, which means that we are demonstrating data about 7 input files. Then you will see that there are 4 information, that is the auxiliary 0, which means the auxiliary properties are px. Capital Px means the polarization in the x direction, similarly in the polarization along the y and z direction, along with the overall polarization and the absolute value. So in case of sodium, the first 3 columns indicate the position of the atoms, and the second 4 and the rest of the 4 columns indicate information about the polarization. Since you see in our structure the core and the shells are in the same positions, so polarization did not occur here. But if you change the position of the core and the shells, that means you separate the core and the shells, then you will see that the polarization, there will be a value for the polarization of the structure. So this is the main basis of today's lecture, and you can also go through the subsequent options of using shift, duplicate and wrap. and those will be very easy if you just try it by yourself. To understand if your structure is shifted or duplicated, you can simply refer to the .gin file format, and if you look at the positions of the atoms or the number of the atoms, you can understand if they have been shifted or if they have been duplicated. Moreover, to understand information about how your wrap is working, you need to look at the position of the cores and the shells. In this way, you can understand or interpret information about how your options are working on the system. So this would be all for today's video. Thank you.